Thank you. Good afternoon. And I had two other opportunities to come to Lausanne before, when there was an ISIP in the late 90s, and there was an international conference of multimedia and expo. But I didn't know how beautiful this place is, so I always had some other choices I had made without knowing. Some places like Baltimore and so on. Oh, it's being recorded. I should be careful. Anyway, so once I made those appointments and I couldn't get out of them, and I'll see Lausanne, I said, oh my God, what a beautiful place. How come I did this? So I'm happy to be here. As they say, third time is a charm, right? So I'm happy to be here. And I came last night. So US is about 6 hours ahead, and I got up at 2 o'clock today, got some work done, and went back to sleep at 5, got up at 6:30, and I'm here. So when you're a teacher, the thing that you worry about is whether somebody in the audience sleeps as you lecture. Today I'll be a little bit more worried and make sure that I don't sleep when I'm lecturing. Right? So feel free, this is a very interactive session. I've been teaching for 31 plus years. So, and also I'm father of 2 children, 21 and 26 years old. There's no question that you can ask that will upset me, right? You will know when you have children of the age, by then they would have asked you all kinds of questions. So feel free to be interactive. And if you want to come, the front rows is fine. I'm not planning to give any exam or any quiz or anything like that. And okay, so I want to also acknowledge my good friend, Professor Martin Vetterli, who's here. I've known Martin for a long time. In fact, most of us have known him for a long time because of his pioneering contributions in wavelet theory, implementations, and so forth. And good to see you, Martin. That's one thing that happens to you when you're a professor. You are friends with a lot of people, and you see them again and catch up with you, and that's the most beautiful thing in our profession. So today, I thought I'll talk about some of the recent work we are doing on dictionaries, manifolds, and so on. My background is a little strange. I started out as a signal processing person, and about 6 years into that, I became half signal processing and half computer vision. And now I think I'm kind of 80% computer vision and 20% signal processing. But this is a sliding scale. So when I am with computer science folks, I talk about information theory, stochastic process, detection estimation. When I'm with the EE folks, I talk about graph theory, submodular optimization functions. When I'm with both of them, I talk about something else. But seriously, that's how the research is these days. There's no one single discipline that you can hold on to. Things are all coming together, right? Computer science, applied mathematics, electrical engineering, and so forth. So since this is a general talk at the department level, I'm going to give an idea of what the important issues are, what we are doing, and we'll give references to various papers we have published in the last few years. And before I proceed, I want to thank Olkan for making this happen, and it's a pleasure to be here. Okay? Good. So, representation. That's a basic issue. Anytime you have to do a pattern analysis, right? Representation. How do you represent patterns? And it's becoming more important now when people talk about big data. Well, what is big depends on, beholder, right? The eyes of the beholder. But since, even then, when you have a big data, what is the best way to summarize it so that you can do some processing in real time? So representation is a critical issue. So we'll talk a little bit about that. I'll talk about two things, 2 ways to represent. One is purely driven by appearance, so-called dictionaries that come from signal processing side. And I'll talk about manifolds that tries to capture the geometry of the underlying data that comes from computer science and applied mathematics and so on, differential geometry basically. And I will mostly talk about face recognition, classification, and so on. That's where we have applied this, and I'll give you some examples of object recognition. My background, when I graduated from Purdue, was mostly in pattern recognition. When I studied at Purdue University from 1977 to 1981, Purdue University was considered the citadel of pattern recognition. So I took classes from Professor Fukunaga, Professor Fu, Professor Kashyap, and so on. And one of the issues in pattern recognition is that you have this training data set, you design your classifiers, but unfortunately you don't get to use your system. You're going to sell it to somebody, you're going to ship it to somebody else. There's no guarantee that the data that they will have is exactly the data that you designed your classifier with. This is a classical issue of testing data being very different from the training data. So even in the early stages of pattern recognition, researchers realize that this is a challenge. There's no point you have 99% accuracy with your data if it is 30% accuracy with somebody else's data, right? So you see, efforts to improve the classifier structure. If you look at chapter 2 of Dura, Hart, and Stork, they'll talk about how do we make nonlinear decision boundaries. How do you have nonlinear transformations of representations that you have so that your decision boundaries can accommodate the variations that you will see when you get a new test data set. The whole idea of SVM blossomed, and SVM also became even more popular the moment you kernelized it. Because when you want to think about nonlinear transformation, there is the issue of what is the best nonlinear transformation. Should I take x1, x2, x1 square, x1 cube, x2, blah, blah, blah. Kernel trick said, no, don't worry, wherever you have inner product in your classifier, replace it by a kernel function. It could be a nonlinear function, a Gaussian maybe, tangent hyperbolic or polynomial. So immediately you were able to generalize the complexity of the decision surface. The hope is that when you do that, you will work well with the training data set. So domain adaptation is the cousin of transfer learning that is very popular in machine learning, in natural language processing, which basically recognizes the fact that the distribution, probability distribution of the training data set is going to be different from testing data set. So how do we cope up with it? So that is something that we started a few years ago in ICCV 2011, and it's getting a lot of attention. Many others are working on it. So I will talk about that in the context of generalizing dictionaries as well as manifolds. So if you feel, please feel free to ask questions. This was at Purdue 1981, and this is me, right? I had a lot more hair. I go to the same haircutting person near my neighborhood. I've been going to her since 1991. Their rates are going up. My hair is going down. So I said, how is this? You have to give me a little discount. You don't have a lot to work with. She's a very smart person. You know what she told me? Well, in those days you had a lot of hair. It was like mowing a lawn. I didn't have to think much. Now you have patches here and there. It's like a landscaping. That takes more effort. A landscaping person charges more than somebody who just mows the lawn, right? Anyway, that's all right. But, this is Professor Kingston Fu. How many of you have heard of him? He started this syntactic pattern recognition. This was on a weekend. Professor Fu liked wearing jeans during weekends, and this is Saturday. And this is my advisor, Professor Kashyap, Ho Kashyap algorithm. Some of you may know about it. This is Professor Asriel Rosenfeld. This is Professor Tom Huang. A lot of us in image processing know he was at Purdue when I was a student. This is Professor Fukunaga. I like to show this picture because these days, if you are not in Google in the last 2-3 years, you pretty much don't exist. Right? Sometimes I go to a meeting and I ask, who is this gentleman? Of course, people 50 plus, they know. But for young people, it's important that you know about these pioneers. Every field has pioneers. Information theory has Shannon, right? Pattern recognition has these fantastic people, and I got to work with every one of them in various ways. And it had a big impression on me because they were founders of various fields that I got interested in. They also were not only pioneers, extremely generous to their graduate students. Okay, so I know you have great professors here, so you should not have a problem. But I think you should also feel fortunate to be in a place like this. Because we don't realize it when you're a student, but when 10 years later you realize all the education you got. So I really am grateful to all these guys because, I think Hillary Clinton wrote a book on saying it takes a village to raise a child. It really needed all the brain power to teach me something, right? So the major points again, testing data come from different distributions. So we'll talk about domain adaptation. And also, depending upon where the data lies, metrics matter. Because sometimes you may want to see if this pattern belongs to this pattern or is similar to this pattern. So you have to come up with metric. So if it is on vector space, then we kind of know what to do. If it is on a structured geometric space, then one has to think about geodesics and so forth. So I will take two representations, dictionaries and manifolds. Motivation, well, we worked many years ago on a problem where we wanted to know if we can tell who the person is by the way they walk. You may know of your uncle or an aunt who kind of walks a little funny, and you can pick them up at 50 meters. And we all code that information, okay? Actually, I have a signature for how Martin walks. So we were sitting in the restaurant in our table, and Martin walks by. I just saw a glimpse of him. I said, there is Martin. And other guys were all kind of looking for him, and he kind of went somewhere, and he's talking his telephone. I said, no, I'm pretty sure I saw Martin. Yeah, he was there, because I have observed him. I've known him for a long time. So we code this, right? So how do you develop a computer algorithm for this? So what we do is we subtract the moving person, and we have the silhouette, and we put points of high curvature, normalize it. That sits on what is known as a shape manifold. So if you have a picture of me like that, a video, I'm hopefully somewhere here, and this is somewhere else, and so on. So if I want to recognize or verify the other person, I should be able to compare patterns on a sphere, which is no longer Euclidean. So you have to come up with a different metric, right? That's where manifolds come. Now here again, we have a video of a football, Georgia Tech football. I don't know if the video works. Let me try. It should work, but sometimes. All right, yeah, it's okay. Can imagine the players moving, right? Okay. So the idea here is we want to find, by given maybe 30 frames, what kind of play is developing. If you're a football expert, you will know right away. And here, there's not much resolution. You cannot look at a person, he has a helmet. The uniform is not of much use because these guys all have the same uniform and sort of. So in terms of the motion patterns, I can very quickly say whether it is a defense play or a pass play, which kind of a pass play. So that also can be done using Riemannian manifolds. And this is a data set where you have a video of a person walking through in this corridor and slowly turning towards the right, left. So how do you recognize this person? As you can see, this is really not a very friendly picture, right? There's a lot of shadow and so on. And so these are some of the problems that we will discuss. And we recently finished a 5-year effort on how to do face recognition or verification at 50 meters, 100 meters, 200 meters. The idea was to do it in a maritime environment. So I used to take my whole group to Baltimore Inner Harbor. We will be in one boat with sensors, cameras, and my students will all be in the other boat. And they didn't mind because it was fun. They were not working in the lab. And I also bought them lunch. So, so they will go around, and then I will take their pictures. Now, I am moving because I'm on the water, right, water waves, and then they are moving. Sometimes at that distance, they may be even out of the frame. So I have these long lenses and take their pictures and so forth. And since they're all computer vision students, they knew that they have to look at the camera, because face recognition works when you look at the camera. But still, some of them wanted to give me a hard time. So they wore hats, there was a blur and so on. It's a nasty problem, right? So you need good representations. Now, dictionaries are not new to signal processing people, okay? I would say wavelet-based representation is a form of dictionary. So it's been around. Of course, Steve Malla, wrote a book on matching pursuit, and many others, they extended that. This is a colleague from my department who published a paper on this. And these are more from the representation point of view. And Saito and Kaufman and one of my students, we thought we will come up with a method for building, dictionaries for separation of signals. So we did using Fisher's linear discriminant analysis, since my background is pattern recognition, and did a wavelet packet as a representation to separate signals, one-dimensional signals, two-dimensional signals, and so on. Now, then what happened right around that time, these guys came and said, why do you want to restrict yourself to these known signals like DCT and wavelets and so on? You have a lot of data. It's not big data then, it was a small data, but you have data. Why don't you build your representation straight from the dictionaries? So that's where the things turn. So modern day, this is what happens, right? Signals as single images, sparse coding comes into play. And also in computer vision, we like to make big things from small things. If you have a human, then, of course, you can have a human model, but we also say maybe we should have a model for the head, for the hands, for the legs, for the thighs, for the torso, and put them together. So compositional representation is very highly valued in computer vision. Parts-based recognition. You have an object has parts. Can you describe parts individually and then put it together using geometry, right? So it's computer vision. So that is possible, so we like that, and there are methods for updating them as more data comes in. But then, what you do for images, this is where I tend to have some fight with my image processing friends. They say, well, computer vision is just an application of image processing. I say, no. Computer vision, image processing looks at 2D image, and computer vision, the holy grail is, we have a model for how the image is created. We have the 3D world, we have a source of illumination, we know where the viewer is from, we sometimes may know the property of the material, how much of light it reflects and so forth. So we can actually start with the 3D model and produce the image. Computer graphics guys do a good job of that. But they are also very clever. They do the forward one. Given a model, they can make it more and more complicated and produce pretty pictures. Computer vision people, they do the inverse thing. Given the picture, they want to know what is in the scene. Well, that's why they are usually unhappy, because it's a much harder problem. Because you have an image, you want to estimate the 3D surface normals, you want to estimate the albedo, the kind of a texture map that says how much of the light is reflected, and sometimes you may have to know where the source of illumination is and so on. That is too much to get from one single image. That's when the regularization framework came in the mid-90s and so on. But the point is, when you want to do dictionaries for face recognition, you got to be able to accommodate for variations that you see in a dictionary, in a face, for example, in a face. Illumination, it makes your face look different, right? Pose, frontal, non-frontal, expression, occlusion, and so on. So those are the things. So you cannot straight away take things from signal processing, image processing, and apply to computer vision. It gives you some performance, but you got to work harder. Okay, suppose this is the work inspired by this paper from Berkeley and Illinois, Wright, Ema, Shankar Sastry, and Alan Yang, and they have another recent one in 2011. The idea is this: suppose I have 5 pictures of Okan and 5 pictures of everybody here, so I can create this guy, DK, right? So for one kth person, I have all of his faces. Then I have L such folks, then I can combine them all together. So I just keep it for now. And then I show up as Y. Then I say, well, my face I'm going to say is a linear combination of all the faces I have seen. Yeah, maybe. Right? Okay, because if you're actually a pattern recognition person, if you do this, they'll kill you. Because you cannot say a new picture is a linear combination of old pictures. It's not true. That's okay. Let's assume that. So I can write it y d alpha. What happens if y turns out to be exactly one of the xij's? Then what happens? Just the alphas corresponding to those are non-zero. Everybody else is 0, ideally. If I just kind of transplanted myself and sat there, and again I come back here, same illumination, same everything, only those alphas are non-zero. So what do we have? Alpha here is a sparse vector. So I can now figure out a way to estimate alpha. This should be actually 0. Find alpha with the 0 norm, the one that has the least number of non-zero components, such that my assumption y d alpha is satisfied. Of course, 0 is not good for computing, so we replace it with L1 norm. And there are papers that talk about under what conditions L0 and L1 norm are close to each other and so on. There's a nice work from Donahoe on phase transition diagram and so forth. So basically what I do is I have my D from the training images, I have the test image, and I try to optimize this, get this. And once I have the alpha, then I will go and resynthesize using this equation for each person, and then take the difference between y and the synthesized one, maybe take a reconstruction error as a criterion, and I say this guy looks like somebody who is already in the data set. Okay, this is the basics of how dictionaries are used for face recognition. Now, of course, we don't want to keep D straight as everybody in the training data set, because the training data set can be huge. So what do we do is you can now introduce any technique that you like. There are a couple of techniques you can use. KSVD is one. The other technique is method of optimal directions. And we have developed some new techniques based on information theory and so forth. That's going to appear in FAMI. But nevertheless, you can just take the dictionary KSVD. This is a very well cited paper. So in case if you are interested, you can take a look at it. So B is the data, D is an initial dictionary, tau is a sparse matrix, and you go through the standard method in terms of basis pursued, and then there is a second step which updates the components in the dictionary using a singular value decomposition. So there is a method that's available given a lot of training data to come up with a second representation of the training set, and then you can pretty much do the classification as I mentioned. If the faces were always seen in frontal, if the faces were always seen in great illumination, no occlusion and so on, you can stop here. Problem is solved. But it's never the case. So we want to now introduce some robustness towards illumination condition. So that's when this model comes. I is the face that you see, rho is the albedo, n is the 3D model, s is the surface source direction. This is how the face is created in a very simple way. Very ideal assumption, very ideal assumption. Okay, suppose if somehow given a picture, I can estimate surface normal and the source direction and albedo, then I can recreate multiple images of the same person, which I can throw into the dictionary learning algorithm, because it gives me additional robustness. As you know, why people with big data now have more money? Because they have more data to train their stuff with. Right? Here, I have one image, I don't have a lot of money. So I try to create whatever I can from a single image. So this is what I'm saying. If I were in a very rich company, I have access to millions of images, I can just go and do the one, I don't have to worry about it, right? But I also like to say, data does not generalize. Models do, right? Anybody agree with me on that, or you want to challenge me? I can have 1 billion frontal images, faces. I cannot tell you how the side view will look like or off frontal will look like. But if I build a 3D model from the 1 billion images I have, I may have a better idea. So if you want to impress your girlfriend or a boyfriend with a quote today, just tell them, data does not generalize, models do. If they're still your friends, lucky you. Okay, good. All right, now, yeah, this is what happens when you're a professor for 30 years. You start spewing out these quotes, which kind of look at the first hearing very profound. I hope mine are, but anyway, don't worry about that. So this is the picture how it is done, surface normal, albedo, blah, blah, blah. But I want to go this way, right? Okay, of course, you formulate this. I was telling at lunch today, sometimes you can only do what you know how to do it, right? So what do we do? If you're a signal processing person, you will say, this is an estimation problem. Let me somehow try to write it as a Wiener filter kind of a thing, which we learn in our graduate classes. Okay, so I start with the given image, and I start with some initial 3D model. Hey, face 3D models, have you seen them? They kind of all look the same. You all have nose popping out, eye sockets going in, right? So you can just choose any one of those models. Whereas database has several of them. And there are methods for estimating source direction given an image. We have done work on that. Pentland has done work on it. Multiple people have done that. So you start with this equation and then you play with it. So what happens is you can then write a very simple equation. This is what you have from the given image. This is the true albedo you want. And then you have all these guys. And this. So this becomes a kind of a filtering problem, the signal dependent noise, which we all know from doing image restoration is something that we can do. And this is where your EE background helps. Remember I told you? When you're with CS people, you do EE things. This is what you do, okay? And then you can basically estimate your rho, and then you can start relighting it. Okay, this is estimated albedo. Now you can see the original image has variations in illumination. This guy doesn't have those. Of course, the first estimate will look a little funny. That's fine. We always seem to have a problem in this region because the pixels are very dark here. So all our folks need some kind of a nose job after they do the shape from shading algorithm. Now you want to relight them because I want to create more artificial examples. How many should I do? Well, Kriegman at San Diego and his group showed you just have to do 9 of them. They showed you can arbitrarily synthesize given a picture, and they also indicate 9 source directions. It's all given to you. So if you have the model, once I have albedo, there are methods available for estimating the surface shape. Okay, this is standard shape from shading approach. And you can also use the fact if it is frontal, the face is symmetric and make it constrained and so on. So all I'm saying is, how you build dictionaries for signals will be a little different when you have to think about handling variations in the patterns that you expect to see. You have to accommodate them. That's it, right? So this is a simple example of how we can handle for illumination. We have a paper in image processing transaction last year where we handle in-plane rotation and scale by building dictionaries in a transform domain. And then we also have a paper on how to do it for out-of-plane rotation. You can't go too much for out-of-plane rotation. There's limits to how much you can do. Fine. So those are the ways you have to kind of embellish your signal processing techniques to account for what happens with pattern changes. And so of course we have to run a lot of these data sets and so on. Some of these data sets people have reached already upper 90s, 95, 98 and so on. So that's another thing we are seeing in computer vision these days, what we call as solving data sets. So if you go, we have a lot of standardized data sets and everybody is trying to beat each other up by 2-3% improvement, and somewhat similar to what happened with compression literature with PSNR improvements and so on. Okay, but the data sets are becoming more challenging. So you can't impress people now with 98% on a pi data set or things like that. So that's good. Now this is the resolution issue. So if I have a phase at let's say 50 meters, 100 meters and so on, there are a lot of pixels in the surveillance cameras and they're also not in good condition like this. So you can now develop, traditionally people like to do super resolution. Super resolution works if you have multiple images, if you have perfect alignment and so on. Otherwise it introduces its own artifacts. And you sure cannot go more than a factor of 2. If you can go by a factor of 4, you should consider yourself lucky. Okay, without additional information. Okay, so, but what you can do is you have high resolution gallery, you can always dumb them down. It's easy to go down, then go up with the resolution scale, and you can build dictionaries at multiple scales and so forth. Okay, so the performance is not, so you may ask the question, is face recognition solved? Well, there is going to be a paper called Deep Face at CVPR 2014. Facebook folks and somebody from Israel, Blair Wolf, I think, they are claiming 97.3% in the LFW data set. This is faces in the wild. These faces were acquired from YouTube videos and pre-processed a little bit, and it's a tough problem. The best method that does not use deep learning is from Columbia, from Peter Bell-Humer's group, 93.7. Now if you look at the deep face paper, instead of the traditional neural networks where we had a layer, hidden layer 1 or 2, and then the output layer, here they have as many layers as you please. Of course we don't know exactly how many we should have, but more layers and tons of parameters, 126,000 parameters, something like that. Tons of data, of course, Facebook. You all gave data. When I ask data for my research, you say, oh, my privacy, I need IRB, this and that. And you all put your pictures on the Facebook. And what happens? They design a very good classifier and they beat the crap out of me. I'm sorry, this is recorded, right? We have to edit that. But all I'm saying is, that's what's happening, Data rules. Google has numbers. So there's an interesting question, right? So how do you handle? But I like, even if you get a few percentage less, I like what we do because we tell you what we do, right? But here, there are problems. There are problems where the performance is not there. Look, I still have only 70%, 67%, because this is a challenging problem. And that's what professors should be doing, right? We should not be doing, assuming we're in academia, we should not be doing easy ones. We should be doing difficult ones that others may not like to do. So face recognition is not solved. It is solved with some caveats. So if you want to do research in face recognition, go for it. Okay, we talked about still, but a lot of video faces are available, right? Surveillance cameras, etc., etc. They produce videos. So you will think, hey, video should be easy because you have more data. You know what? That's not always true. It is true a little more. There's more data. But it's not like I'm standing here and you're taking a video, you have multiple shots of me and I turn like this, you take some shots like this, like that. No. I'm moving around. But you have to track me. In the Navy, the remote recognition problem, we couldn't make our tracker work because we couldn't detect our things. Sometimes the face will disappear from the scene and so on. So what we did, we detect the faces in each frame, and we did association using conditional random field. So because you may not be even able to track. So video-based face recognition is not as easy as it looks like, but it's getting a lot of attention. So we build dictionaries for videos. We cluster them based on their pose, there's illumination and so on, and basically did the same thing. And these are the numbers. This is the same MBGC data I showed you. And originally it was all bad, everybody it was doing bad, and we are slowly getting at the 80th percentile. And then in a different protocol, we have to also go in the mid-90s. If you are not in the mid-90s these days, it's not going to cut it, right? So you have to somehow get there. But this is a very difficult data set though, from University of Texas, Dallas, where there's illumination is a problem, people are walking, they don't always show their face to the camera. And here, the best method you can see is, depending on the different assumptions you make about how many subjects and how many videos, we are going all the way from 20. So this problem is still a challenging problem. So there's a major initiative that's been launched to do kilo hours of video-based face recognition problem. It's a very challenging problem. So if you are interested in doing that as your thesis, you should really look into that. Okay? Now, so this is some more results. So we have done a lot more things on dictionaries. The reason why I like them is that you can do nonlinear versions. Very simple mathematics gives you 5%. Okay? You can do dictionaries using transform domain to give you some invariance. And also, one of the things that we like in computer vision, right, there is multiple levels. There is a semantic level, there is a feature level, and so on. We want to do something which is in a structure preserved dictionary learning. Expressions. We have major expressions. There are about 44 facial action coding system that Paul Elkman taught about many, many years ago, but most of us work with 6 expressions. Sad, some bored, some happy, some angry, right, etc. But each one of those expressions can be decomposed in terms of action units, individual muscle motions. We know, not we, but people have done experiments and said, these action units combine together to produce this expression. So there is a structure. It's not just loose. So can you now learn action units as well as expressions in a 2-tier way, representation, structured representation. It's like doing line and edge detection at the same time. All right? Okay? So we showed that, and that is important because this hierarchy is something that computer vision people are very, very proud of. Okay? So we have a paper on effective computing, and then that's this guy. Okay, and then we also have figure ground separation. Some of you may have taken Amtrak if you are on the East Coast. So we have a project with the Federal Railroad Administration, fault detection, concrete ties and so forth, because people take a lot of pictures. Somebody goes and inspects them. They want to know if this can be automated. We have models for cracks. We have models for good ones. So you can build dictionaries for both, and then you can do source separation. Figure ground segmentation is a basic issue. You can do that with these dictionaries. So that's because you have data, right? So you can build dictionaries, and that's something we discuss here. And then in the 80s, if you are aware of this research, given a 3D object, there's always a question, what are the best characteristic views of this 3D object? Should I keep all views, or can I just keep 6 or 8 of them? This is a classic paper by Chakrabarty and Herb Freeman called Characteristic Views. But it was coming purely from graphics point of view. You can now bring this sparse representation theory, signal processing theory, and given a 3D object, what are the salient views? So you can bridge the geometry and signal processing. Otherwise, the existing technique, what it does is it does SVD. As you go around the object, whenever there is a big jump in singular values or vectors, it says, I need that image, I need that image. Okay, so you can bring in all of this. Other thing that you can do is, what if I have multiple signatures? Say I have my face, my fingerprints, my iris. They're all from me. Can I use them? The fusion is another big deal that everybody talks about, right? You can have sparse representations for each one of them, and you can combine them in the sparse latent space using the fact that they all come from the same person as a constraint. So finally all of them, you know what happens? They all become optimization problems. That's why you should take Olkan-Shevar's course. The most popular course in my department at Maryland, graduate course, is the course on convex optimization. Every fall, 50 to 60, 55 students take that. So if you still have some course credits that you have to do that. It has now become so important. It's amazing. Okay. So I'm going to just move over to the next topic. Dictionaries are kind of imagey things, right? They're not features. They're kind of imagey things, appearance things. But computer vision is not all about that. A simple problem, you know, for example, if I want to estimate your age, the two approaches I can do. One I can do is I can extract points on your face, and there are models to say how these fiducial points will change as you become older. There are two kinds of models, age 2 to 18, and then there are models that come a little later, and of course in my age group models are very complicated. Age 2 to 18, mostly related to bone shape. You know, we put fiducial points. Somebody did studies how these points vary as the kids become adolescents and so forth. And the model they used is a water-filled balloon that gets pulled by gravity. So I like to say when we were born, we were all round, and then we slowly become oval shape. That's why when a grown-up man has a round face, what do we say? He has a baby face. Okay? Somehow gravity didn't work there. I don't know why. But the point is, we have a model for it. Now that model starts with fiducial points. And if I can normalize the fiducial points with respect to scale and translation, then it will sit on a sphere. So I can start regressing on a sphere, or regressing on a Grassmann manifold rather, sorry. So we can build models like that for age estimation, right? It's becoming very important. So that's one example. So face recognition across aging can be used manifold. I also talked about activity recognition. Expression analysis the same way if you are using landmarks. Now if you have videos, you can also have dynamic texture models. These are variations of the good old time series autoregressive models across temporal domain. And the matrices that show up there have specific properties. They are orthonormal matrices. So if you want to compare one parent with the other parent, you should know what the geodesic is for the orthonormal matrix. You cannot treat them as Euclidean representation. So, and then we have shown how they are useful for spatio-temporal alignment and group activity recognition and so on. Let me take a very simple example to promote the idea of manifolds. This is activity recognition. So I have somebody walking, maybe running, blah, blah, blah. What we figured out is a few years ago that the kind of transformations that will happen, I can walk slowly, I can also walk very fast. Should I call that two different actions, or should I say they are the same thing? This is a classical dynamic time warping problem in speech. That I speak slowly or fast, right? It should be the same word. So we realized with respect to action, for every action there is a particular warping function. It's almost like how many different ways I can jump into the the seat, right? I can jump straight like this. So if you put trajectories on that, there are many different trajectories, but the action is jumping into the seat. I can go from my parking lot to the department in many different ways in trajectories, but the action is the same. So these are the kinds of things where we use. So what we do is we normalize and so on, and then we can do what is known as a Procrustes fit to figure out what is the representation for the landmarks. So you may know about this guy, Procrustes, who ran a cheap motel. He had one size bed. The bed, let's say, was 6 feet long. If you are 5 feet 4, he stretched you so that you will fill the bed. And you don't want to know what your height if it were 6 feet 2 inches. Yeah, okay? So basically the idea is you represent these silhouettes, patterns, the points on the silhouettes, and they become on the manifold. Now what I want to do, I know there are multiple different ways of doing the action. I would like to come with one average representative and also have a PDF on the possible variations, because then I can design a Bayes classifier. So that's what we do here as normal trajectory is this guy activity, and then we know that because of the underlying mechanism, physical mechanism, the transformation is a diffeomorphism. Okay, it's basically goes, the variation is characterized with this function. So the model parameters are the average trajectory and the distribution. So if I want to get this distribution, let's assume, I like Gaussian, let's say. So I want a curved Gaussian because it's sitting on a manifold. So I need to know what the mean and what the covariance is, right? Once you specify the mean and the covariance, the Gaussian distribution is specified. So we basically have to estimate these, and the question comes, what would be the particular form of the manifold you want? What we decided was, this is the work done with Professor Anushree Vastava. So we take the square root of the warping function, derivative of the warping function, because then if you take the L2 norm of it, it is 1, and therefore it is on the unit sphere, and this is also known as Fisher-Rao metric, and Steve Maybank, another computer vision researcher, has also used it. This is about the geometry of phi, we don't need that. Now I need a representative for my activity, and what is done here typically is what is known as the Karcher mean, okay, which is described here. And the Karcher mean is not a unique one. There are multiple ways, and there is some simple distance calculations you do for measuring what the Karcher mean is, and then you can go through and calculate the variance. Now some of these things you see here as exponential inverse are the transformations that happen when you go from the manifold to the tangent plane. Now once you have these two things, I have given several realization trajectories of the same action. We can estimate A and P, and then once you have the mean and the variance, you can go ahead and estimate your PDF and do classification. So this is a very simple example of a manifold based method, and it appeared in 2009. Many versions of this. So but the idea is very simple. You have features that don't sit on Euclidean structure, they sit on a sphere, or it can be Grassmann manifold or a Steffel manifold. Then you have to come up with the appropriate distance measures for separating one pattern from the other. The reason why this becomes useful will come later when I discuss domain adaptation. So for now, let's assume manifolds are good. So the data set that we showed, this is a so-called INRIA data set, 11 actors performing 13 different actions from multiple views, and of course, we are in the upper 90s and things like that. But we have done a lot more with this. This is a bit dated. We have done group actions with these kinds of methods. We have done video clustering using dynamic texture models and bringing geodesics into calculations and so forth. So manifolds is something that's being looked at very carefully. So these are some of the things I will refer you to in the PAMI paper, IJCV, Nibs, and alignment manifold. Basically here we consider the spatiotemporal alignment on a Riemannian manifold, and talks about it, age estimation and face recognition, because when you use fiducial points as features, then manifolds place into picture. And if it turns out you have a lot of data and they're all sitting on a manifold, you want to do nearest neighbor search, what is the technique and so on. So this is so differential geometry is getting some play in the computer vision literature. Now I'm going to now start the third topic, where I'm going to bring all of these together. So this is a data set taken from a paper in ECCV by folks at Berkeley. This is what we call a source domain data. X, labels, or Y. Then we know it is a cup, it is a glass, it is a mug, it's a shoe, and all of that. This is what we call as target domain data. We don't know the labels, or we may know the labels for some. If we don't know any labels for the things in the target data, we call it unsupervised domain adaptation. If we know some labels for targets, we call it semi-supervised adaptation. Okay? Let's look at, there is also transfer learning that people know in natural language processing. Domain adaptation is somewhat related to it. The assumptions are that the marginals are not the same, but the data, label given the data is same. So these are some subtle technical things, so it's okay. So how do let's first take the most difficult problem. let's assume I have labels for everything in the training data set, right? You do Amazon Turk, pay people and get labels. Some of them are not right, but we have them. But then I have the new data set, I have no idea what the labels are. That's unsupervised. Suppose if you have, let's take the simple case, face recognition, right? And I don't really have an annotated data set. So how would you do that? I'll take all of your faces, I vectorize it to a PCA and decide to keep top 100 coefficients, the corresponding eigenvectors. Take every one of you, express using that and get your biometric code. And then a new picture comes. I will take the picture, expand it using eigen things, get the coefficients, and whichever is closer, I'll say that guy looks like that guy. Right? Now, how do I design SVM? Before I do SVM, I have to know exactly who you are. Because linear discriminant analysis, SVM, they all separate one pattern from the other pattern. So I have to start with 100 phases of A, 100 phases of B, etc., etc. So PCA, while it looks like a very simple method, when I did the PCA, I really didn't care about who you are. I just cared that you all have a face. So what I'm saying is, if you are unsupervised way, PCA is not a bad idea. Nothing else is there. Because if nobody gave you face image with labels, unless you sit down and annotate them, how are you going to design linear discriminant analysis, right? So now, so here when we did the unsupervised, that's all we decided to do. We said, let us take PCA. Okay, before I go to the manifolds, let me show how we will do with the dictionaries, for example. I have a source data set here, and I have a target. So what I do is I construct intermediate domains and intermediate dictionaries, such that the initial dictionary will represent this very well, the final dictionary will represent this very well. Then I have a lot of intermediate dictionaries. Then I can project all the source data and the target data with respect to those intermediate things, get their coefficients, align them, get a feature vector and do a domain adaptation. This is a very simple way of using dictionaries for domain adaptation. Now how does it work? So this is the algorithm. D0 is initially the source dictionary, and then I bring in the sparse coding idea that is present in KSVD, and then I have an increment. So dk plus 1 is dk plus a delta. So you can build incremental dictionaries. Now if you have these dictionaries, you can also synthesize intermediate representations, because given a dictionary, we know how to synthesize original signals. So the goal is the final one here will be a good approximation to the target. So you are trying to interpolate between source and the target data. Okay, so that's one way to do. And once you have all these intermediate dictionaries, you do classification like you before. The feature vector is long, depending on how many different intermediate representations you have. And how does it work? Well, it seems to work sometimes, and sometimes it doesn't, right? So this is our performance, and these are some of the other methods that are available. So this is like saying, I have a frontal face data set, I have a side view data set. Okay, given only frontal, how would you design your classifier so it works on the side view? It's not going to be good. But if I gave you a lot of faces for 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, thousands of faces. For each such rotation, you can build PCA. And then you can take everybody in the source and represent with respect to each one of them. You get a long PCA, biometric code. Same happens to the target. Hopefully one of those two things will match and give. This is basically what Pentland did in the early 90s. Eigenviews. So what we are now doing, I mean, think about it. Eigenface is a very simple dictionary. Okay? Eigenimage, eigenface is a simple dictionary. So what we are doing is bringing sparse coding, so you are a little smarter about how you build. So the intermediate representation. Now, this is another challenging data set, so-called office data sets. And the performance is not great yet, but it's getting better. So I talked about unsupervised domain adaptation. And I said, if you don't have any target label, PCA is not a bad thing to do. So we do the subspace. I talked about if you have intermediate data set, then I can do PCA view 1, view 2, view 3, and the problem is clear. But what will I do if I don't have them? What will I do if I just have the source and the target, the frontal and the side view? Is there a way to somehow manage it in the unsupervised framework when I don't have any labels on the target faces? Well, let's construct PCA. You have the subspace, and they sit on what is known as a Grassmann manifold. The beauty about Grassmann manifold, if I know I am in one point, source, and then the target in the other point, I know how to traverse the manifold, go from source to target along the geodesic. I can sample along the geodesic. I can get intermediate representation as though I have the PCAs at those intermediate places. And then I project the source and the target onto those bases, construct a long feature vector, and do the matching. That's the one that we did in ICCV 2011. It's going to be a PAMI paper soon. And that created a lot of attention. You know, somebody said, Rama, you're being too stingy. Why you do finite such things? Why don't we do infinite interpolation between source and target? And there's a lot of mathematics that goes with it. So this is basically the idea. And so this is afternoon, 3 o'clock, 3:15, 3:30 now. We all need a cup of coffee before going through all these equations, but I won't do that. You have a PAMI paper, just Google under my name. It's there already and you can read it. But it is becoming an important field now. There's just a lot of papers coming. So the question is, how does it work? Slowly we are getting better. There are various scenarios. You can assume I know 10% of the labels on the target, I know 0% and so forth. So more you make assumption, the better it gets. But still it's a challenging problem. We're all still working on this particular data set because we have to get upper 90s and then we say, hey, I don't need you anymore. We go and take another data set and start at 60% and slowly work our way up 90, and then it's like divorcing a data set, right? After spending some time with it for a while. But it's a challenging problem. There is semi-supervised, and there is semi-supervised was a little better, obviously. And then we have multi-domain adaptation. If you look at even earlier pattern recognition works, it's not necessary that you have to represent a class by a single distribution. It can be multimodal, Gaussian, right? So multiple domain is somewhat like that. And so the life goes on. Okay. These days, what's happening in our vision conferences is that you have to be very laborious or labor intense to get your paper in. A couple of years ago, we wanted to do a problem called sensor adaptation. Iris sensor. There's an old sensor. You enroll millions of people, and suddenly the company says, oh, I have a better one. And then should you enroll all the million guys again on the new one? Or you think you can generalize from the old to the new? So this is what is known as a sensor adaptation problem. We have a PAMI paper this year. How did we do it? We said as long as there are two samples of the same person, either from sensor 1 or sensor 2, or if one of them is from one sensor, other from the other sensor, it shouldn't matter, it should be same. So you can put it in what is known as a multiple kernel instance learning stuff, again optimization. So we saw some improvement. Well, you have to show it works. So University of Notre Dame has a data set, 104 gigabytes. My student, as most PhD students, said, I'm not going to spend all my time running on this big data set. He just ran it on 1.6 megabytes of data, something like that. And we sent the paper to PAM. The reviewer said, hey, how do I know that you didn't give me the best result on one segment and maybe it flopped on all other segments? Go and do it on the full 104 gigabytes. He comes, his face was longer than usual. I said, hey, you want a paper in PAMI? You got to do what PAMI guys want you to do. So he spent another month, we ran the whole 104 gigabytes, showed improvement. So that's what you all have to do. When I graduated, Ladies and gentlemen, I had a PDP 1145. I shared with the 30 other PhD students. My images were 32 by 32. I had the Lena image 128 by 120. I split it into 4 blocks. I individually worked with them. I put them back together. But now we have gigabytes, terabytes of data, and we have 18 different algorithms working on those with numbers. So if you get into the area, you got to show you are better at least by 3% by state of the art. You can't take the most recent one and do it, because if the reviewer is somebody whose method you did not compare with, although his or her method may have produced lower percentage, you still have to compare. So get ready. Right? Everybody is excited about big data, sure, but not the students who are going to run experiments. Anybody seeing this already? Hello, anybody seeing this already? A lot of experiments you have to run on different data sets with different algorithms and compare and say why you are better than what's out there. That's fun. You should have graduated in the 1980s. Like I did, or Martin came a little later, 1984. The data was small. So there's something. Okay, now there are many ways to adapt dictionaries. I showed you one simple, intuitive way. You can also learn some shared representations. You know, the way I can explain source target. We all dated the person we eventually married. So we are source and they are targets. Distributions are very different. Right? How do you get along? How do you even decide to get married? You find common things. Things that can generalize. That's what this is about. Find representations that are common, shared by both source and target. Okay? And so that is what we call it latent space. Because we really don't know how we are doing it, but we sure are doing it. Otherwise our marriage is not stable. Honey, you don't like coffee? Oh, that's okay. I don't like coffee too. I won't say that. Anyway, you got the picture, right? But this you can explain successful marriage with projection onto a latent space. There's a theory for it. It's not just some Dear Abby thing, right? And all right, so there's a paper we have in CVPR 23. So take a look at it. Point is, it becomes an optimization problem. We want the projection from the source data to a latent space, projection from the target data to the latent space. We have a fidelity criterion. Of course, if you are a pattern recognition person, you cannot be pleased with just doing reconstruction. You have to add a discriminative term. So we want to separate the in-class guys from the out-of-class guys. But after everything said and done, it's a convex optimization problem. Numbers are good because it's a CVPR paper. As you can see, my student has to compare with the ECCV 10, our paper ICCV 2011, CVPR 2012, etc., etc. List goes on. This is amazing. We had our paper in November, ICCV 2011, CVPR 2012, which happened 7-8 months afterwards. They already had improvements over ours. So that's what's going on. Well, a lot of open questions in domain adaptation. How do you know how much shift there is? How do we know how different our partner is from us? Right? If the partner is just like us, likes Seinfeld, likes espresso, likes vegetarian meal, and I'm good. I don't have to adapt. If my partner doesn't like coffee, only likes tea, and is totally non-vegetarian, I have an issue. Right? So, how do we know? Should we over-adapt? Because if I over-adapt, then I'm not happy. I'm not me anymore. I'm the other person. But we don't have a metric. We know in computer vision pose is a problem. How bad? We can have an idea. Illumination, how bad? We have an idea, but there's no actual characterization of how much domain shift there is, and we need to look at that. And also, the domain adaptation problem is defined in terms of the PDFs being different from source and the target. But when I did the intermediate subsampling along the geodesic or dictionary or latent space, I threw away the PDF. I never mentioned that. So I want to know when I go along the geodesic whether I'm really starting with the PDF of the source and converging with the PDF of the target. I have no idea. But we are kind of slowly looking into that. It looks like the Monte Carlo Markov chain particle filtering problem. The source can be your proposal distribution, target can be your other distribution. So how do you go along the trajectory? Staying on the manifold all the time. So those are some other things. So I hope in the time I had, I don't know what the time, yeah, exactly 1 hour. Yeah, because I usually charge more money when I go after 1 hour. Just kidding, just kidding. Okay, we talked about dictionaries. The idea was dictionaries is a concept, came from signal processing. But if you want to apply to computer vision, you got to add some bells and whistles to it to handle elimination pose and all that stuff. Manifolds capture geometry. Mathematics is a little more trickier. Especially statistical inference and manifolds is tricky. But there is a beautiful book written by Professor Chikusi. It's called Statistical Inference on Special Manifolds. It's a very nice book. You should read that. And dictionary-based methods, of course, these days when you do something, if you don't tie it to what's happening in the brain, it's not worth doing. Right? Deep learning, the basis for it is that brain has multiple layers. It's not to make fun of it. It gives it some basis. Otherwise, it looks very ad hoc. It looks like just some kind of a technique we pulled out of the hat. And people have looked at sparse coding in terms of what happens in our human brain. And domain adaptation is so fundamental to what we do. You teach what a cup looks like for a 2-year-old. You can put the cup upside down, you can roll it, you can cover it under a newspaper. Ask the kid, where is the cup? There it is. Puts that thing and shows it, right? So the kid doesn't get confused if you take the cup from the living room and put it in the kitchen. No, cup is a cup. We do that. So domain adaptation is very fundamental. So, in the 1983 we had the first computer vision conference. Before that we used to call it PRIP, Pattern Recognition Image Processing. I attended 1978 and 79 in Chicago. 81 was in Dallas, 82 Las Vegas. That was the last one. Computer vision people said, we don't want to go to a conference that has image compression, image restoration and so on. So IP was removed. PR they kept, because people who worked in PR were they're loudmouthed. They were going to scream, bloody hell. And so they said, fine. CVPR, 1983, first time. In those days, PR was one session. CV was everything. We had shape from shading, stereo, motion, structure from motion, feature extraction, object recognition. Name it. Pattern recognition was some fingerprint, some document thing, and they used to complain. Oh, we don't have enough representation. We don't have enough representation. Then what happened? SVMs came. We have data, we have features, we have SVM. It immediately gave 85% for pattern classification problems. So computer vision people said, wow, this is good. So now you go to CVPR, more than 70% of the paper, the last page is SVM. So it's not, CV is not there much. It's all ImageNet. You might have heard about ImageNet. Like classification, Caltech 101, Caltech 256, phase, this, everything is now pattern recognition. So it's good because I started off as a PR, pattern recognition, and then I became signal processor. I became computer vision. I'm going back to my old place, pattern recognition. This is what happens if you're a professor for 30 plus years. Finally, you will end up with your PhD thesis topic. You start with that and you will end with that. And it will take you all this time. Say, oh God, why didn't I stay there all these years? No, I'm just kidding, right? Now, data and computing. Big data is there, fine. But I told you, I like to say this. It looks very profound to me. Data does not generalize, models do. I think we need to come up with a compromise. We should not just get swayed away by just, oh, I have this plenty of, because we won't have. You will not have 100 million faces at your disposal. Who will have a couple of 3 companies, 2, 3 companies? So we just will never be able to. But humans generalize from very small data sets. So let's look at methods that generalize from small data. Let's not worry about, big data, because at some point our biggest will not be big enough compared to somebody else who has access to data. So I think being able to build models, it doesn't have to be a face model, but model of whatever we are trying to figure out, right? So that you should never lose sight. Don't think just by just running a lot of data to the algorithm will be done. And math is coming back. Everywhere math is much more sophisticated these days. So take a lot of classes in differential geometry, Riemannian geometry, statistical inference and all of that. And I think you have to thank my generation. Right? We built all the cameras, not me, but my generation. I'm being careful. All the big computers we have given you, all the sensors we have given you the data. More importantly, we have not yet solved the problem. It's a big gift. If I have solved everything, what is there for you to do? So exciting times are for you. That's what I tell everybody. When I try to recruit high school kids who want to join EE, I show them my iPhone. iPhone 4. I said, why don't you break it and see what's in it? I say 60%. Since I have a material science professor, now I reduce from 85 to 60. Because I was first saying 85, he said, hey, how about me, material science? So 60% ECE, 20% maybe material, and then maybe 15% mechanical engineering, because they have to build a nice case. You can erase that. But I also tell them, they may be very savvy with 2-thumb thing. And I think if evolution is right, 50 years from now, everybody will have 4 thumbs. Because you need that many to do it, right? I still do 1-finger thing. I'm gone. I tell them, you can do how fast you want to do, but who gave you those iPhones? I said, your uncle and your dad. Remember that, right? So, we are giving you everything. We have told you everything that works and doesn't work. So, go and get it done, guys. Thank you. I'm happy to take questions. Yes. Yes, sir.
So if we take the data set you built for face recognition, the one with the silver and gold,
yeah.
And you are similar to the face recognition, but just with swap faces, without context, without shape.
Yeah.
What is the success rate?
If we have not done that because we have to put the data onto the Amazon Turk and so on, the privacy issues and so forth. But there are some results. I think for LFW, they say humans achieve upper 90s. Okay. Now, but you have to be a little careful though. When humans do, they bring other things. I know context is not there, but familiarity. If I have all those people in the board, not my students, but if I had Julia Roberts and Tom Cruise and President Obama and so on, it will be very, very good because we recognize familiar faces. We still do not know what it means to a computer. It's not just having a lot of training data. So, if you look at the Deep Face paper, which is now available on the website, they do make a claim that they have a computer algorithm that matches the human performance for that data set, which is in the upper 90s. So, this data set, we couldn't send it out because IRB issues and so forth. So, but yeah.
Other questions? So how much of this is boiling down to optimization in the end?
If you are, there are two views on that. If I'm not very good at optimization, I'll tell you it's a small part. But every optimization problem, as you know, is a little different, right? I mean, you can pretty much do with standard tools available, right? But I think I like every optimization to be kind of a little different because the constraints are different. And so I think there is plenty of scope. That's why that course is very popular graduate course in my department. And everybody should do optimization class now in EE. It's very important. Sparse coding, dictionary learning, you name it, it's there. Yeah, it's a big part. Yes?
Data do not generalized models do, right? If I go tonight to my kid and say that story to my kid, they will say, I don't care because my Facebook account recognizes 99% of the faces anyway, so I don't need your method. Right?
Yeah.
What should I answer?
That is tough. But what you say is, you recognize the people you know. There are people you may want to recognize that you have not seen before. So tell him his friends are not the only ones in the world that he should be concerned about. Is a good answer? Yeah. So if that were the case, yeah, I agree. But you can also tell him that he may be able to visualize his friends in totally different light, or make their noses grow 100 feet tall, long, change their expressions, put the mouth over the nose. He would love doing that.
Or change their ages, right?
Models, yeah, or age them. There are softwares available, right, for aging. This is interesting. The aging thing, there is an agency in US that I'm sure everywhere, missing children. Milk cartons, their pictures come. Suppose a baby is kidnapped age 5, they want to know how the kid will look like age 10. There is no computational model. They go to the kid's family and get pictures of the grandparents and parents and sisters and siblings at age 10, Photoshop. So far, the machine has not found the similarity. Another human did. So the director of that center came and gave a talk at Maryland. He told of many different ways they found. There's one case where the girl sees the picture in the cartoon and goes home and tells her mom, I think this girl is in my class. It was not a computer. How can a computer do? A computer doesn't have access to all the faces in the class. A human does. And how she figured out? We don't know, because the actual person's face doesn't look like the one in the cartoon. There's something that clicked, especially with teenagers. Girls, they do all kinds of things with their hair and this and that. I have a daughter who is 21, so I know. Right? So they don't look like that, but humans somehow got that. And the story is, the mom then calls the headmaster and says, this girl seems to be in your school. The headmaster calls the girl and says, hey, are you this person? She says, you better talk to my mother, And then they realize they have been found. So she goes home and she says, Mommy, this is what they're saying. Oh, okay, we have to leave. Of course, the girl, being a teenager, wants to come back to school and say bye and hug all her friends before she leaves. The police was there, and it's nothing serious, Turns out the mother kidnapped the child when she was young, and because of separation. And so the point is that there's, the simulations, they don't work that well, right? So you can tell your son he can have fun. Models do better, but we don't know what the right model is. That's the problem. But at least in face we kind of have an idea. But think of all the other things where big data is available, which are very complex, and what kind of models we don't know. But just data alone will not cut it, I think. I hope so. At least for the next 10 years when I plan to be doing research.
All right, maybe we should do our apero and continue the questions in the break.
Thank you. Thanks for your time.